Okay, good morning. How's everyone doing today? More students than usual in person. That's good to see. Okay, so I want to wrap up mesh current analysis today. We have one example. I will go through the example, and then there's also a slide on the supernode, which is not as confusing as the one for your slide on the super mesh, not on the supernode. Super mesh is not as twisted as supernode. Okay, all right, so let's share and okay. All right, so chapter 2, section 2, chapter 2. All right, so we stopped here. Let's do a brief recap. Mesh current analysis, the steps involved are: first, identify all the meshes, assign mesh currents, and you can choose any direction you want for the mesh currents. Typically, if you look at any book or if you take a class with any other professor, all currents are typically in a clockwise direction. Okay, typically in the clockwise direction. And again, this is something that I've been doing for several, decades. And so I always choose a clockwise direction. Then you apply KVL to each mesh to generate equations. Third step, apply Ohm's law, express each voltage, each resistor voltage in the mesh in terms of the mesh current. Okay, it is very similar to the node voltage analysis. Node voltage analysis, we use the current equations or KCL to generate our equations, and then we apply Ohm's law. We do the same thing here. We identify meshes, assign mesh currents, apply KVL to each mesh, generate our equations, then apply Ohm's law to each resistor voltage and express it in terms of the mesh current itself. V equals IR. These with the mesh current. And then you solve the equations. Okay. All right, so let's take a look at an example. Several of you have, several of you, when I say you, I mean students. All of the students in all of my sections have, begun working on the homework. Some of them have even completed it. Problems are straightforward. They are not very long. They don't take multiple steps. So again, once we get through the example today, I will end up putting a due date on this, leaning towards putting it down on Saturday. If someone else needs more time, they can let me know. Yes. This is homework 10. 10? Mesh current? Okay, I'll change the dates on there. So all three sections I had announced. Oh, that's why lots of students got it done. So as I said, at the beginning of the quarter, I have to assign due dates. Otherwise, the system will not display all the homework assignments to the students. So I have to typically enter some arbitrary dates depending on how I think the class is going to go. And then once the topic is, introduced or covered in class, that's when I change the due dates. And again, I announced this on Wednesday. I announced this on Monday, announced it last Friday also. So most likely the homework will be due either Saturday or Sunday. I was leaning towards Saturday, so let's see how it goes. Okay, so we solve for all the mesh currents in the circuit. We won't solve all the resistor voltages. I will show you one resistor voltage and current. VA is 10 volts, VB is 9, VC is 1, and this is 5 ohms. R2 is 10 ohms. Actually, let's not do that. 10 ohms. R3 is 5 and R4 is also 5. Okay, time to choose the mesh currents. And as I said, I always typically choose a clockwise current. Since I already have A, B, C, and 1, 2, 3 in there, I'm going to use X and Y. So X, IX, and IY. Again, those are just notations. You can choose whatever you want. So identified meshes, there are only 2 meshes in here. Very easy to see. And then assign mesh currents IX and IY for both. We'll call this mesh 1. And let's call this mesh 2. Okay. And both currents are clockwise, IX and IY. So let's see. I don't want to use that pen. All right, that works. Let's take mesh 1. In mesh 1, I have 4 voltages: VA, VR1, VB, and VR2. Okay, 2 resistors, and then the voltage sources. So I'm going to write, and again, my KVL direction is also clockwise. So I'm summing voltages in a clockwise direction. I will have minus VA plus VR1 plus VR2, plus VB plus VR2 equal to 0. Sum of the voltages should equal 0. Again, KVL can be clockwise or can be counterclockwise, or you could take all the voltage sources on one side and all the resistor voltages on the other side. Whichever way you're comfortable with, you stick with that. Then VR1 expressed in terms of Ohm's law. So this is from KVL. This is Ohm's law. VR1 is IX times R1. VB is, of course, the voltage source. And VR2 is a result of 2 mesh currents, IX minus IY times R2 equal to 0. Okay, IX minus IY times R2. When you are in mesh 1, and your current IX is going in the clockwise direction and IY is going the opposite, again, because they're both clockwise in both the meshes, they're going in the opposite direction. So if they're going in the opposite direction, it's IX minus IY. If both were going in the same direction, which is the assumption we make at the beginning of our analysis, if both were going in the same direction, I would have IX plus IY. Okay, but let's not get into that. It's like the node voltage analysis. You can choose whichever direction you prefer for your branch currents. Is the same thing here. You can choose whichever direction you want, assume a direction, and then your analysis depends on that direction. If you want to keep things simple, then choose clockwise for every single mesh current. And then when it comes time for the shared resistor, all you do is you look at which mesh you are in. if you're analyzing for mesh 1, then the current for mesh 1 will be positive. The current that is not in that mesh will be negative. Hence, Ix minus Iy. Does that make sense to everyone? Let's take a 10-second pause. Think over that and let me know if you have any questions. Any questions at all? Okay, let's move on to mesh 2 then. Actually, wait, let's plug in the values before we move on. So minus VA is minus 10 plus R1 is 5 ohms. So 5 times Ix plus 9 volts for VB. And then this is going to be R2 is 10 ohms. So 10 times Ix minus 10 times Iy is equal to 0. KVL, Ohm's law, plug in all the known values, reduce the equation to the form of AX plus BY equal to C. So this becomes minus 10 plus 9 is minus 1. Take it on the other side, and I have 15 Ix minus 10 Iy is equal to 1. I'm going to call this as equation 1. Equation 1. Easy enough, or rather straightforward enough, right? Then let's move on to mesh 2. In mesh 2, I have, how many do I have? 1, 2, 3, 4, 5 voltages. 3 resistors, and 2 voltage sources. Starting from the bottom left, going clockwise direction, I have a little bit more towards the left. VR2, this time it would be minus VB plus VR3 plus VC plus VR4 equal to 0. Okay. Account for all 5 voltage. So first count the number of components in the loop, and then you have to have that many quantities in your equation. So VR2 minus VB plus VR3 plus VC plus VR4 sum up to 0. Then apply Ohm's law. And from Ohm's law, now we are in mesh 2. So Iy is positive or negative? It's positive. So now VR2 becomes Iy minus Ix times R2. Understanding this is the key to make sure that your analysis, to ensure that your analysis is correct. Okay. In the first mesh, it was Ix minus Iy. The same voltage when you do, when you apply KVL for mesh 2, becomes Iy minus Ix. And you can sit there and derive this expression from the explanation I gave in last class, right? You have 2 mesh currents going to the same branch. Point of entry is plus, point of exit is minus. When you do that for Iy in mesh 2, that becomes plus and minus. And here it is minus and plus. And then this is minus VB VR3 is not shared, so it's 5 times IY plus VC plus 5 times IY equal to 0. And there's a side note in this equation. I'll come back to it once we finish the solution. Plug in all the known values. R2 is 10 ohms, so 10 times IY minus 10 times IX minus 9 plus 10 times IY plus 1 equal to 0. Rearrange the terms in the form of AX plus BY is equal to C, and we obtain this expression. Minus 10 times IX plus 20 times IY minus 9 plus 1 is minus 8. Take it on the other side. You get 8. I'm going to call this equation 2. 2 unknown variables. I need at least 2 equations. If I had 3 unknown variables, I would write a third KVL equation, and then I would have 3 equations to solve. But 2 unknown variables, IX and IY, 2 equations, solve them with any method you want. These values are simple enough. I can do them by hand. If I say equation 1 times 2 and equation 2 times 3, I would obtain 30 times IX, minus 20 times IY is equal to 2. And then this would be minus 30 times IX plus 60 times IY equals to 24. Add the equation, get 0 plus 40 times IY, so 26. IY is 26 by 40, 0.65 amps. Did anybody else do a direct solver in their calculators or an online solver? You get the same values? Okay. And then you plug this into any one of the equations, either 1, 2, 3, or 4. And I would get, let's see, if I plug this into equation 1, I get 15 times IX minus 10 times 0.65 equals 1. Therefore, IX equals 1 plus 6.5, so 7.5 divided by 15. And therefore, IX is 0.5 amps. All right. Write it down, think over it. Let me know if you have any questions. Did the procedure and the steps make sense? Right? You identify the meshes, apply mesh currents, assume a direct from the mesh currents by applying KVL. Then apply KVL and generate equations, plug in all the known values, reduce it to a linear equation, and then solve using any method you prefer. See, in a quiz, and especially in the final exam is you'll be doing it on paper. so you won't have access to the internet. So you better be able to solve this on your calculators. Okay, so practice these methods. I'm letting everyone know in advance right now. Okay, so once you have these currents, Ix, let's take a look at R2. That's the only shared branch, right? So what do I have for R2? I have Ix going down this way, and I have Iy going up. Ix is 0.5, this is 0.65. Mesh currents, again, to repeat that point, are not real. They're hypothetical. They do not exist in real life. So what is the actual real current that is flowing through R2? Or which direction is the actual current flowing? Is it going up or down? Up, up. Question? Or are you just saying up? Well, so I got two ups and one down. Ix is 0.5. So to determine the direction, we just look at the values. In this case, we are not concerned with anything else going on in the circuit. We simply take that component, which is the resistor R2 in this case, and we have two hypothetical currents going through that or flowing through that component. So then we look at which current has the larger value. And that's it. Whichever current has the larger value, well, wins, for lack of a better word. And so the current is actually flowing in the upwards direction. And the value is simply the difference of the two. So it would be Iy minus Ix, which is 0.15 amps. So again, once you have the values for the hypothetical mesh currents, then you simply isolate that component and look at the values for the two currents. If they are in the exact same direction, you simply sum them up. Your job is easy. But if they're in the opposite directions, as will be the case if we choose clockwise directions for all, then the branch or a shared branch will always have currents going in the opposite direction. Then whichever current has the higher value is the direction for the actual current through that resistor. In this case, it's Iy. Iy is higher than Ix. 0.65 minus 0.5 gives you 0.15. That's the current flowing through R2. And once you have that, you can find voltage VR2, simply 0.15 times 10, 1.5 volts. And then you can solve for the resistor voltages and the resistor currents in all the other branches. Okay. R1, R3, and R4 are straightforward because it only has one mesh current flowing through it. So the mesh current Ix and Iy are the currents flowing through those resistors. Right? R1 only has Ix. So current flowing through R1 is Ix. Does that make sense? Right? And then Iy is the same thing. Iy is flowing through R3 and R4. It is not a shared branch. And so the mesh current is the actual current flowing through R3 and R4. All right, let's take a 10-second pause. Think over it. Let me know if you have any questions. Problem 3 is actually very, I was knotted up over that because I hadn't reviewed my notes. But once I reviewed my notes, it's like a one equation answer. Because it's, so the question being asked was about, oh, now the camera is moving. Interesting. There's a camera at the back for like Zoom meetings, I guess. I don't know. It's like moving on its own right now. So the question being asked was about the homework problem that has a current source, I believe here, and I believe here, right? This is the one you're asking about, and there's a resistor here. So a student had already asked me about this, and I was trying to, wrap my head around this, and I overthought the process. But if I have, and I choose mesh currents going in this direction, clockwise for this, and just in the same direction for that current source. Well, this resistor is a shared branch, right? So I have two currents. I have one going down and one going up. But I look at the current source, and I only have the mesh current. That's it, nothing else. So the mesh current for this first loop and for this third loop, or the third mesh, is the current source. And that's it. You just write one KVL expression for this middle mesh, you plug in the values and you solve. And that's it, one equation answer. I think it takes less than like 5 minutes. Does that make sense to everyone? Because the resistor is a shared branch, the actual current is I1, and then of course, if I choose I2 here, it's I1 minus I2. But the current source is not shared with anything. Okay, it is only shared, it's not shared with any other mesh. It's a single branch. So if I choose my mesh current as having the same direction as that current source, I have my answer for that mesh current. And that's it. Now, taking that one step further, if a current source is shared between two branches, so let's say as an example, if a current source is shared between two branches, for simplicity's sake, let's call this 1 amp. And I have my hypothetical mesh currents IA and IB. Now it's shared, so the current source can be expressed as a difference of these two mesh currents IA and IB, similar to the resistor currents. Make sense? And in this case, IB is going the same direction as 1 amp, so I would write IB minus IA is equal to 1 amp. That would be an expression, that would be an extra equation I could use to solve for the unknown voltages and currents. It's similar to node voltage analysis, where if you choose one end of the reference, one end of the power supply as your reference node, then you automatically have an answer for the node voltage at the other end. And it's similar to that. I have an extra equation that I can use to describe the relationship between the two mesh currents. All right, 10-second pause. Think over that. Let me know if you have any questions. Any questions? Okay. All right. So if super node didn't rack your brains, well, let's go to super mesh. But this is actually easier than super node. Okay. Thinking back to the beginning, I said a mesh is a simple loop, right? Mesh is a simple loop. It does not contain any other loops inside it. So think of super mesh as simply an electrical loop that has a mesh inside it. Okay. And the reason why we do that is, again, because we have a shared branch right here. The current source is in the middle. If the current source is in the middle and we apply KVL around this loop, let's call this M1, M2, and M3. If I apply KVL in M1 and M2, I cannot express the voltage across that current source using Ohm's law. Right? KVL in mesh 1 and 2, I cannot express the voltage across the current source in terms of Ohm's law. So I would have an unknown here, and I would have another unknown here. So what do we do? Well, we simply eliminate that, and we apply KVL around the outer loop. So we combine both the meshes together, and you apply KVL to the outer loop. Eliminate the current source. Apply KVL to both meshes together as one loop. All you're doing is you're applying KVL on the outside of both meshes. That's all. So again, super mesh concept, even if you don't understand anything, meaning how it's derived. When I say don't understand, what I'm saying is how it's derived. So derivation is not important, but all you're doing is you're applying KVL to the outer ends of that mesh. That's all. So let's not get bogged down into the derivation. Okay. Simply apply KVL in the outer loop. Now you have resistor voltage, and then voltage sources. But the thing that you have to be careful about is that the mesh currents do not change. So if I was to apply KVL in the outer loop for mesh 1 and 2, KVL around M1 and M2 is going to give me, let's see, I1 is on the left. Let's draw this out. I have 4 voltages. I'm going to write 1 ohm times I1 plus I1 minus I3 times 2 plus I2 minus I3 times 4 and plus 10 volts for the voltage source equals 0. Your mesh currents still stay the same. You got I1, I2, I3, I3. So just because we eliminated that current source does not mean we get rid of the mesh currents also. Those mesh currents and the direction that you chose at the beginning of your analysis, they still remain the same. Again, important point, right? Don't change it in the middle of our analysis. So now we have eliminated the current source. We write an equation, and then we write a separate equation here. and then we solve. If we don't have enough equations for the number of variables, we can do one more loop on the outside. That would be an even bigger super mesh. Again, the whole point is we should have sufficient equations or a sufficient number of equations to solve for our unknown variables. In here, I have 3, I1, I2, and I3. So I need at least 3 equations to solve for them. Yes. Yep. Yep. That's from the previous example. And here, so the point being made was we can describe 5 amps in terms of the 2 mesh currents. So I2 minus I1 would be equal to 5. So we don't even need a third equation here. We can express either I2 or I1 in terms of the other. And then you plug it back into one of the 2 equations, and then you can solve it. Does that make sense to everyone? All right. All right, any questions? Yes. Yes. Yep, that'd be fine. The question being asked was, can we go on the larger loop on the outside? And in this case, the larger loop does not mean the biggest equation. If we look, how many components are there in that big outer loop? 1, 2, and 3. So we have 3 ohms, 1 ohm, and 10 volt source, only 3 voltages. So the equation is actually smaller. So the equation for this big outer loop is smaller than the equation that you take for this super mesh. Because this super mesh right here has 4 quantities, the equation that we just wrote right here. But if you write an equation for the big outer loop, there's only 3 quantities. Again, as an engineer, it's up to you to choose the best and the most efficient method. The less number of quantities we have, the less the chances of error. Okay, any other questions? Any questions at all? Okay, so mesh current analysis. Again, I'll put the due date. Again, 3 problems on there. The third one we just covered in the previous slide. It's like 5-minute, it's like a 5-minute analysis. Today is what, Wednesday? So Thursday, Friday, and I'll put it for Saturday. So it's about just a little bit shy of 4 days. I think that's more than sufficient time for it to get done. Quiz on Monday, I'll announce on Friday also, but announcing it in advance. We'll do mesh current analysis on Monday, next Monday. And then depending on, let's see, superposition. Yeah, superposition. We might end up doing a little bit of superposition also. Okay. All right, so before I move on, any other questions? Yes. This one, let's see, 2 series, not in series, not in series, not in series, not in parallel. I don't see it, no. Yeah, it's not possible. The question being asked was, is it possible to simplify the circuit or, reduce the circuit? But it doesn't seem possible. Which brings us to the superposition principle.
Hey, Professor.
Actually, yes, go ahead.
Wait, can you repeat when the midterm was?
Midterm, there's
Is
no
that
midterm.
Oh, okay. Sorry, I thought you had said that. My bad.
No, it's only quizzes. Quiz on Monday. Every Monday there's a quiz. And no midterms in my classes. We can have one if students want one. All right, superposition principle. Simply states you can break up the circuit into individual parts, analyze each part independently, and then you simply add up those quantities to get the actual final answer. Okay, that was just the gist of it. Let's get into the actual gritty. So we are doing circuit analysis, right? Circuit analysis is the determination of the unknown voltages and currents in a circuit. If we have one source, we know that the voltage or current at any given point in the circuit is a result of that source alone. But if we have more than one source in a circuit, similar to the previous example where you had a current source and you had a voltage source. So it doesn't matter if it's a current source or a voltage source, or if there are two voltage sources, two current sources, or 10 voltage sources and 5 current sources, does not matter. If you have more than one source in a circuit, then the resulting voltage or current at any given point in the circuit is a result of all of those sources acting together or working together, right? And that's what we did with the node voltage analysis and the mesh current analysis. Here, in this example, we had 3 voltage sources, right? VA, VB, VC. So the current through R2, which we found as 0.15 amps, is a result of all 3 sources, A, B, and C, working together, right? So superposition principle states that if that's the case, of all 3 of them working together result in a voltage or current at a point in a circuit, we can break up the circuit into individual parts and analyze the circuit for each source working independently. Okay. If you have 2 sources in the circuit, you break up the circuit into 2 parts. You analyze the circuit for each source acting independently. You find the point of interest and the quantity of interest at that point, which is either the voltage or the current for that particular component. And then you simply add those up together. That would give you the actual voltage or current in that circuit. So if I have n number of sources, then the resulting voltage or current at any point is a result of those sources working together. So you break up the circuit into n parts. You analyze, and n is basically the number of sources in there. And you analyze the circuit with only one source working at one time. Okay, you analyze it for only one source working at one time. Now, the way we do that is by reducing all the independent sources in a circuit to 0. And reducing a source to 0 simply means you take a voltage source and you replace it with a short circuit, and you take a current source and you replace it with an open circuit. And we will see how we do that. Okay. If you have a voltage source in a circuit, and let's say at the other end you had a current source. Okay. What is voltage? Voltage is the difference in electric potential between any 2 points, right? If both points are exactly the same potential, then the difference in potential between these two is 0. So the voltage between these 2 points is 0, right? So for a voltage source to be 0, we replace it with a short circuit. This way, if you measure the voltage, let's call this A, B, C, and D. If you measure the voltage VAB, is now 0 volts because there's a short circuit between A and B. And so you measure the potential for both points is exactly the same. And so neither one is higher or lower than the other. So for analysis purposes, when we remove or we replace the voltage source, we replace it with a short circuit or a wire. And so that means that points A and B are exactly the same potential. Voltage VAB is equal to 0. That's the concept behind replacing a voltage source with a short circuit SE. And the same thing for a current source. For current to be 0, there has to be an open pathway, meaning if there's an open pathway, current cannot flow through. If current cannot flow through, it is 0. And so to reduce a current source to 0 would mean you simply open up these terminals. Now current flowing through ICD is equal to 0. Literally no current can flow through. If there's no pathway, current cannot flow through. And so current between C and D is equal to 0. And that's the concept behind replacing a current reducing a current source to 0 means replacing it with an open circuit. You simply remove it from the circuit. And then you analyze for the circuit. Okay.
So you can reduce either one and it will
Yes.
still lead to the same result.
Yes. So this is two sources in the circuit. Because I have two sources, 1 and 2, I break up the circuit in two parts. This is part 1, this is part 2. And then I analyze the circuit independently and I find quantities. In this case, let's say this was R1, R2, R3. If I wanted to find, let's say, voltage across R1, if VR1 was the question, then VR1 is now broken into two parts. VR1 due to the voltage source, let's call that Vs, and the current source as Is, plus VR1 due to Is. Part 1, part 2. Okay, so if I wanted to find the voltage across any resistor or any component, I would have to analyze it twice. Well, actually, I have to analyze it n number of times for n number of sources in the circuit. If I had 3 sources in the circuit, I would have to analyze the circuit 3 times just to find one quantity. Okay, just to find one quantity. 3 separate analyses to find one single quantity. It's important that students understand that. If I wanted to find VR2, I would have to perform a separate analysis. And the same thing, VR2 is now in 2 parts. So Vs and VR2 due to Is. Same thing if I wanted to find voltage or current for IR3 is also 2 parts. So IR3 due to Vs and IR3 due to Is. Does that make sense to everyone? So as you can see, superposition is I wouldn't say simple. We reduce it to a simple circuit. So our analysis is simple. but it is highly inefficient and laborious and time consuming. If you have two sources, yeah, okay, we can break it up. We can do twice as many analyses as we need. If you have three, still within reason, but if you have four or more, then you can see how your time would keep multiplying. Does that make sense to everyone? Okay. The point of using superposition is so that our analysis, individual analysis, is easier because we can then apply any method we want. Simplest to apply would be series parallel analysis, where we reduce a large network of resistors down to one single network. So, topic of superposition has been introduced. At least take a crack at it if you have some time today or tomorrow. And then Friday, we'll look at an example. And then I'll post a due date for that homework, perhaps Sunday or Monday or next week. All right, so we'll end class here today. If you have any questions, I'm around. I will have office hours later today. So again, have a good day, and I'll see you all on Friday.